So A subarray, all the values of the elements in A subarray should be less than or equal to the pivot element. Then all the values in the B subarray should be greater than the pivot. Yeah. So that's the condition. Yeah. So then we start growing S region, L region. Yeah. So let me continue. All right. Step number 5. Now, these 3 elements in the U region in white color. So 3 and 5. Yeah. 3. So when we process it, we compare it with the pivot element. Compare 3 and 4. Yeah. We know 3 is smaller than 4. So we should put it in the S region, smaller. Yeah. So we grow the S region. So we color it in red, in yellow. Yeah. But the green region separate the elements in yellow color. So we need to use the swap operation to, put all the elements in yellow in the, consecutive locations. So let's do the swap. Swap 7 and 3. After the swap, you can see, all the elements in yellow color, they occupy the consecutive locations. Yeah. All right, the last element, 5. Compare 5 and 4 greater than 5 greater than 4. So we should put it in the L region in green color. No swap for it, yeah, because the elements in green region, they automatically take the consecutive locations. All right, but after that, we finish scanning all the elements. For the last step, we need to put the pivot element in place. Yeah. Put it in place. Yeah. Another swap operation. Yeah. We know the pivot element should be between S region and L region. Yeah. In between, yeah, as the boundary of those 2 regions. Yeah. So you can see the swap operation should be between the first element in the green region, then the pivot element. So after this swap, then we put the pivot element in place. And it separates 2 regions, the S region, L region. And we get A subarray satisfying the first inequality, A of I less than equal to P, and then B subarray satisfy the second inequality, P less than B of J. Yeah. See, we complete it. Yeah. Here, we use the minimum extra space, right? Yeah. So the extra space, we use it for the swap operation. It's minimum. Yeah. And we do not need to use auxiliary arrays. Yeah. So we eliminate 2 auxiliary arrays. So we save a lot of memory space. Yeah. This is just one partition step. When we do recursion, we keep doing this kind of partition step. In every recursion, we do this partition step. All right, yeah. So then, divide and conquer. Then we can complete the quicksort. Okay, yeah. So that's the whole quicksort. Okay, yeah, all right. Yeah. Now, after that, then, but this is a visual understanding, right? So we use a diagram, so we understand a partition visually. Yeah. But in programming, you need to find a way to control the regions, right? Yeah, control the regions, yeah, especially S region, L region. Yeah, so it's very easy to control. Yeah, yeah. So we just use two indexes, index variables, so we can control these two regions. Yeah. I variable, index variable, and a J index variable. Yeah. You know, the location of the last element in this region. Yeah. To control these two regions. Yeah. For S region, it occupies the array locations with indices from 0 through I. Yeah. L region, the part of the array locations with indices from I plus 1 through J. Then, every time, we only need to change I value or J value to grow these two regions. Okay? Yeah. All right. So before the final in-place step, the pivot step. Now, all right. Change I and J. Yeah. So every time when you need to grow S region, then you need to change I. And every time when you need to grow L region, you need to increment J. Yeah. That's simple. Okay? Yeah. All right. Yeah. Because when you do swap operation, you need to modify I and J. Yeah. All right. Yeah. So that's the, implementation details. Yeah. All right. Yeah. So we complete implementation details of the quicksort. Yeah. Its main partition step. The remaining recursion, just automatic. Combine, trivial. Trivial, right? Yeah. So combine. Do nothing. Yeah. Yeah. All right. So next, we want to look at the best case, worst case. So let's look at the worst case efficiency analysis. Yeah. Yeah. Then best case. Yeah. All right. So for the worst case, first let's look at this question. For what kind of input you will get the worst case? Yeah. So for different inputs, you get different cases. Yeah. So for the worst case, based on our experience, yeah, at this point, because we have discussed so many different worst cases, best cases, so we should have some ideas. Yeah. Remember, I mentioned that balancing principle before. Yeah. In order to get the best worst case efficiency, yeah, we should distribute the data as even as possible. Yeah, in a balanced way, in the most balanced way, in order to get the best worst case efficiency. Yeah. Yeah. All right? Yeah. Yeah. So we do in that way. We do in that way. Yeah. But the input, because here, if we use our standard partition step, right now we have our standard partition step. we discussed in D.4. Okay, yeah. If we use that partition step, yeah. Then when the input data forces us to make unbalanced partition, unbalanced, yeah, because some special input data can force our algorithm in an unbalanced partition result. That could happen, unbalanced. So let's look at what is the most unbalanced partition result. Yeah. All right. Other than the pivot, all the elements in one of the two regions. That's the two extremal cases. This is the first extremal cases. Other than P, all the elements in yellow color. The second extremal cases, yeah, this is S region. Yeah, we can call S case. Okay, all right. The second extremal case, other than P, all the elements in green color in L region, and we call it L case. Yeah. So these two extremal cases give us most unbalanced partition result. If for every partition step, if you have the one of the two extremal cases, then at the end, you get the worst case. Yeah. The slowest worst case. Okay? Yeah. So, yeah. Although here you can see the probability for this worst case is very small, right? Yeah. Very small. The probability, very small. Yeah. But theoretically, it could occur. This worst case could occur. Okay? All right. Now, let's look at how many comparisons do we need for this worst case. Yeah. All right. In one of the two extremal cases, after you do n-1 comparisons, you need to scan. Right? All the elements, each element you need to do one comparison. Yeah. Here we do not look at the swap operation. Let's just look at the comparison operation. So you need an n-1 comparison. After n-1 comparison, what is the problem size reduction? You reduce the problem size. You only reduce the problem size by one pivot element. Yeah. That is the reduction part. Because for the next round, you do not include the pivot element. It's already in place. Why you include it? So you do not need to include the pivot. Yeah. But you need to work on the remaining elements. But the size reduction is the minimum. The size reduction only one size, one smaller. That reduction. Too slow. The size reduction too slow. Okay? Yep. So if you do this kind of slowest size reduction in every recursion round, then eventually, at the end, you will get the slowest worst case. Okay? Yeah. So, and we can find the number of comparisons for this worst case. Yeah. So recurrence equation for the worst case. Yeah. Running time complexity function, every time just one size reduction. Okay? Yeah. So we use the T of n representing the number of comparisons for the whole quicksort. Okay, from beginning to end, this many comparisons. So T of n equals T of n minus 1, because one size reduction. Yeah. And in the partition step, you need to use n minus 1 comparisons. So plus n minus 1. Yeah. This is the recurrence relation. This recurrence relation very easy to solve. You just keep doing iterations. Yeah. Then you will see you need to add up all the consecutive integers from 1 through n minus 1. Yeah. So this n minus 1, the largest constant term, the smallest is 1, right? Yeah. So you add up all these numbers, so you get this many comparisons. So for the quicksort, its worst case is in big theta of n squared. So here you can see the quicksort, its worst case is very slow. Its worst case is not fast. Yeah. And for the merge sort, we know its worst case is much better than this one. Okay, yeah. So for the merge sort, its worst case because the worst case we always do the balanced split. So we won't have very poor worst case, n log n. That's the merge sort. Yeah. So merge sort, you can see one of its properties, it avoids very poor worst case. No bottleneck, right? Yeah. But the quicksort, it does not avoid very poor worst case. This is its bottleneck. Okay, very poor. Yeah. But fortunately, this poor worst case corresponds to a very small probability. Okay? Yeah. Very small probability. Yeah. So its impact is very small. Very small. Yeah. So people still, when we consider the overall performance, quicksort is the best among the current non-sorting algorithm by experiments. When people do experiments, not by analysis. By analysis, it's hard to see if the quicksort is better or merge sort is better. Right? Yeah, not easy to see. Yeah. They are in the same category. They are in the same big theta of n log n category. Yeah. So from the formula, it's hard to see which one is faster. Yeah. But when you run the experiments, you can see, quicksort is faster than the merge sort. Yeah. All right, yeah. So that's the worst case. Yeah. Example for the worst case. Yeah. Let's look at some, input, right? Yeah. So here we go back to the original input. Yeah. So for the what kind of input? So we get worst case. Yeah. Few possible input. This is an array in descending order. Yeah. Descending order. Yeah. Original array. Yeah. Yeah. All right. So if we run the quicksort, using our standard partition step, you can see after one partition we get array state like this. Another partition we get array state like this. Okay? Yeah. Then another partition, yeah. All right, like that. Yeah. At the end, this is the last step, partition. Okay? Yeah. Yeah. So you get the whole array sorted. Yeah. You can see from this simple example, you can see the size reduction, always one size reduction every time. Yeah. Yeah. So it's the slowest. Yeah. So for the descending order input data, you get worst case for the quicksort. Yeah. All right. Similarly, ascending order, you also get the slowest. Yeah. So here I like to point out for the data in ascending order. Ascending order. Okay? Yeah. So here I like to compare insertion sort and the quicksort. Yeah. They're quite different. For insertion sort, for the same ascending order data, it's the best case, right? The fastest, the best case. Yeah. But for quicksort, yeah, here, because it corresponds to one of the extremal cases, so that's the worst case. Not the best case, okay? Yeah. But some people, they gotta, in some kind of intuition. Yeah. So their intuition tells us, yeah, if the given array is already sorted, because ascending order, the whole array, before you apply the sort, it's already ordered. Yeah. Then their intuition tell them that you should get the best case, right? If you by some kind of intuition, yeah, probably false intuition, yeah. So they may feel it should correspond to the best case, yeah. But actually, the result is it depends on your sorts. For some sorts, for example, insertion sort, yeah, it's the best case. But for some sorts, if you look at the quicksort, it's the worst case. Yeah. We know when you apply the sort computer algorithm, computer does not have eyes. Computer cannot see your data. It's already sorted. Computer just implement its code step by step, instructions, going through, all the instructions in your code, then you get a worst case. Okay? Yeah. All right? Yeah. So that's the quicksort. Okay? Yeah. Because we have several such questions in this homework assignment number 2. Okay? So we compare several algorithms, best case, worst case. Okay? In which category? Yeah. For what kind of data? All right? Yeah. So do not get confused. Yeah. All right? So we finish. Yeah, so this is worst case. Oh, yeah. Next, the best case. The best case, this time, we go the opposite way of the worst case. The opposite way, that is, the data is distributed in the most balanced way. Yeah, so let's look at the most balanced partitioning. Yeah. S region, L region, almost the same size. Yeah. That's for the best case situation. Yeah. Then the recurrence relation for this most balanced way. Yeah. Two smaller subproblem about half of the original data size, n over 2. So 2 times t of n over 2. Yeah. Then the partition step big theta of n. Yeah. Here we use asymptotic notation, yeah, but in your computation, you cannot use asymptotic notation in your computation, right? So in your computation, you need to replace this asymptotic notation by some constant c times n. Constant c. Yeah. Then you can do the normal computation. Yeah. All right, yeah. Okay, yeah. Constant c. Yeah. Then, how to solve this recurrence relation? Yeah. So here, yeah, I remember we did a similar way as we did for the merge sort. Yeah, merge sort. Yeah. Oh, yeah. Different from merge sort. Yeah, we use the n equals power of 2 size. Here we use a different way, yeah, because although you can use the same way if you like, yeah, but here I like to use a different way to give you a good estimate. Yeah. So the way is we construct a recursion tree. Then we use that recursion tree to help us estimate the total cost to do the Quicksort for the best case. All right, so let me describe this recursion tree. Yeah. For the recursion tree, when we draw recursion tree, it's a binary tree. Binary tree, many levels, but we need to know how many levels are there in this binary tree. So this inequality helps us to estimate how many levels we can have. Yeah. All right. Yeah. Because this is when we do recursion, we split the array, right? Every time we split array by 1/2. Okay. Split it right in the middle. Split the array. Data size reduced by 1/2 in every partition. So if you keep doing that, each subarray has the data size n over power of 2 number. Power of 2. Yeah. So here, after k plus 1 splits, the data size becomes n over 2 to the k plus 1. Okay? Yeah. But the inequality tells us if the size of the subarray is less than or equal to 1, then you do not need to do any split. So you can stop. Yeah. 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 So that's the last step. So you reach the bottom of the recursion tree. Yeah. Termination. Okay? Yeah. So then we can get an approximate number of levels. Yeah. If we draw the recursion tree, yeah, we know how many levels to draw. It's a binary tree. Okay? Every split, yeah. Before we do split, the non-recursion cost, yeah, because this term is not a recursion, right? So the non-recursion cost, C times N. Then the next level, you have 2 nodes, because one node splits into 2 nodes. So you have two nodes, each node recursion cost C times the problem size. Problem size is n over 2. Yeah. Yeah. But if you calculate the total cost of the next level, it's also C of n. Okay? Adding up. Yeah. Two nodes, also C of n. Then another level split, another round splits. Okay, yeah. Two nodes become 4 nodes. Yeah. And non-recursion cost C times the problem size for each node. So you have 4 nodes, the total non-recursion cost the same C times n, and so on. Every level, the non-recursion cost, if you accumulate non-recursion cost for all the nodes in the same level, you get a C times n. But how many levels? K, right? Approximately K. Yeah, K plus 1. Okay? K or K plus 1. Yeah, K plus 1, but the bottom level, because when you reach the bottom, the data size becomes 1, data size becomes 1, the number of comparison is 0, right? So this, the bottom level, you get a 0. Okay, you get a 0. Then you combine all the recursion cost from all the levels. Yeah. Approximately K times Cn. Yeah. K times Cn, constant C, when you use the asymptotic notation, big theta, so you do not use constant C. Okay, yeah. So the total cost, comparison cost, big theta of n log n. Okay. So this is the recursion tree method you can use to estimate total cost, total comparison cost for Quicksort. Okay, yeah. It's a simple way. Yeah. Simple way. Yeah. So many times when you have a recurrence relation, yeah, you can use this way to estimate its total cost. Okay, yeah. Easier than the way you do the mathematical computation. Yeah. Mathematical computation, because you have to consider when you start with the special case, n is a power of 2. Right? You make a guess. You use the special n, power of 2, to give you a good guess. Then you use mathematical induction. You prove it is correct. Verification. Yeah. That's the mathematical way. Okay? Yeah. So this way, visual approach. So you can also get a good estimation. Yeah. All right, so that's the best case. Yeah. Now we complete the whole Quicksort. Yeah. Whole Quicksort. Okay? Yeah. Yeah. Now you can answer all the Quicksort related questions in our homework assignment. Yeah. I estimate about 5 questions, 4 or 5 questions at least. Yeah. Yeah. So you can answer all those questions. Yeah. With part D of module 4. Yeah. All right. Yeah. So that's the first part. Yeah. Second part. Yeah. I want to do an interesting question. Yeah, so last time, Zach asked me a question. Yeah, after he studied the notes. Remember, we did a question finding the second largest element in the array, right? Remember, we derived the formula. So then Zach tried to use the same way to find the third largest. But, you know, it's not easy to use the same idea, finding the second largest, that method, tournament method. We use the tournament method to solve, the question finding the third largest. Okay. So then he asked me this question at the end of last lecture, Tuesday. Yeah. So at that time, I thought, very hard. So then, when I went home, so I thought about more. So using our previous examples, not today here, I can give you a solution. Yeah. So as the problem solving session, let me solve this problem. Yeah. Because in our homework, our last question, if you look at the last question, question number 25, given 6-element array, n equals 6, how to find the third largest element? That's our, most challenging question in this homework assignment, number 2. Question number 25. Okay, here, I want to derive that formula. Okay, all right, so I have about 30 minutes, so let me use this 30 minutes, to give you the solution. Yeah. So the next topic. Yeah. All right. So here. Oh yeah. Oh, I still have something. Improve the performance. Yeah. Let me talk about that. Yeah, because in the real world applications, you can think about the 2 extremal cases: ascending order, descending order data. Although the probability for the data with that kind of input is very small, but it could occur, right? Yeah. It could happen. Yeah. So then, people feel, we want to do some improvement. Yeah. When we have the data ascending, descending order, those 2 cases are similar, close to those 2 cases, we want to do small modification on our partition step to, make our partitioning perform better. But our modification should be very simple, as simple as possible. Yeah. Here's some idea. Okay. Yeah. One idea called randomization technique. Yeah. Randomization technique. Yeah. So what's that? Yeah. Before you apply the partition step, you do a randomization step. If you do not do the randomization, you use the last element as the pivot, right? Yeah. Last element or first element based on our standard partition step. But if you do last element or the first element, then the data in ascending order, descending order would make your partition algorithm perform very poor. So you want to avoid that. So this randomization step, when you pick the pivot, you do not use the last one. You pick a randomly selected element anywhere in this array, then you swap it with the last element. Okay, one swap. You only need to do one swap operation. Yeah. But you pick the randomly selected element in this array, then you can choose some element near the middle, somewhere, anywhere, then you can avoid, at least you can greatly avoid the two extreme cases, right? Yeah. That idea, simple idea, okay? So random sampling, your selection, do a random selection, any element, anywhere, okay? All right. So select a random element, then do a swap it with the last element or the first element. So then you do the standard partition step. Okay? Yeah. In that way, you can avoid, you can reduce the impact of those two extreme cases. Okay? Yeah. Yeah. But when we do the experiments, yeah, so I remember I assigned a project before, our students should implement randomization without randomization. Yeah. Yeah, but the result is, because if you use the random data, so the array, the data we use, we generate randomly. If you use random data, this modified method performs slightly worse than the standard one, because you need to do an extra randomization step, right? Yeah. But the random data, it's not the ascending order, descending order. Yeah. So for the normal data, not ascending order, descending order, so this method actually it does slightly worse than this, non-randomized method. Yeah. Another improvement called a median of 3 partition. Median of 3. Yeah. So that's another simple way to avoid extreme cases for the pivot. So what's the median of 3? You randomly select 3 elements in the array. Yeah. Random selection, but not 1, 3. After 3, you select 3 elements, you can find the median of the 3, right? Yeah. So that median you use as the pivot. Yeah. Then you can avoid extreme cases, right? But comparing with our first randomization technique, you need to do some more work, because you select 3 elements. Then find a median of 3, you need 3 comparisons. Then you get a pivot. Yeah. So you do a little more selection, preparation work. Yeah. So if you implement this method on the random data, so it's slightly worse than the standard method, because you need to do more work at the preparation, right? Yeah. Yeah. For the random data, it performs a little worse than the standard data. Yeah. Because you need to do more work. Yeah. All right. Yeah. So that's the, some ideas, improvement ideas. Yeah. Yeah. You can use as option. Yeah. But you need to look at your data. So if your data, you may have some significant probability to have the extremal data, ascending order, descending order. Then you can use one of these 2 methods to avoid those extremal cases. Yeah. Otherwise, if your data is pretty much random, then you do not need to use these 2, because you need the extra work, extra preparation work. Yeah. Yeah. All right. Yeah. So that's the further discussion on the improvement. Yeah. All right. Yeah. Yeah. Because the overhead part. Yeah. So you can avoid. Yeah. All right. Then let's go to this one. find the third largest element in the array. To do that, so we need to use some results we did before. So here you can see experience is very important. If you do not have sufficient experience in your problem solving, so many times when you work on some very challenging question, this is a challenging question. But if you have sufficient experience, so you can borrow, so you can, help you get started. Then you can do much better. Here, I want to show you. Here, two previous examples, very useful to help us solve this question. So we did two questions before related to this one. So you need to know those two questions. The first one, find the median of a 5-element array. We did this question before, right? Think about if you still remember the details, idea, how to solve it. That's the first important experience we need to borrow. All right. Second, I think, so find the second largest element. That tournament method, okay? So then, when you have good understanding on the solutions of these two questions, then with some, nice analysis work, so you can solve this problem. Find the third largest element. Okay? Let me show you. I need to complete using the remaining. How much time? 10. Oh, I only have 20 minutes. I need to do a little fast. All right. So first, let me quickly recall the main steps finding the median of 5. Okay? So first, let's recall. How do we finding the median of 5? Okay? Tournament method, still tournament method. All right? So median 5 here, we consider x1, x2, x3, x4, x5. And we do tournament method, so we pair x1, x2, and we assume x1 is the winner of the first comparison, pair x3, x4. For the second comparison, the winner is x3, and if you pay attention to the detail, actually when we run the first round tournament method, we leave x5 out of the tournament. Okay? We do not include x5 in the tournament. for the first round processing. Why? This special treatment is important in solving this problem. Okay, all right. So then, keep doing that tournament method. Comparison number 3, and we assume X1 is the winner. Okay. Now, so after 3 comparisons, let's look at the current status on the data. Use a diagram. So X1 larger than X3, larger than X4, larger than X2, and X5 unknown, larger or small unknown. Okay? Yeah. Then we apply elimination method. Yeah. So after the tournament method, so the first round tournament method. Okay. Then the second round here elimination method. Elimination method because X1 by our observation it is in top 2, right? Yeah, because only X5 has a possibility to be greater than X1, right? Other elements, if not X5, other elements have no chance to be greater than X1. So X1 must be in top 2. If it's top 2, it cannot be the median, right? It cannot be the median. If it cannot be the median, then it is gone, right? Eliminated. It's gone. X1 is gone. Okay? Yeah. Then, after elimination, after the elimination, let's clean up our data. Okay? Clean up our data. All right. Our data after elimination, X3 greater than X4. X2 is here and X5, right? X5. Yeah. But X5, X2, can we pair X5 and X2 for the remaining tournament method? Now we have 4 elements remain, right? 4 elements remain. Can we apply the tournament method again, to do the remaining part of the work? Yeah. But we need to know our goal. We need to update our goal, right? Yeah. Before we do further comparisons, we need to update our goal. Because our original goal is finding the median, right? Original goal. Median. Yeah, let me just write a median. But after the elimination, we did 1 elimination. After the elimination, the current goal, because the original median becomes the second largest, right? Because you remove 1 element in top 2. After you remove 1 element in top 2, then the current goal becomes you find the second largest. Okay, you find the second largest. How to find the second largest? Do you remember we have the formula to find the second largest? The formula finding the second largest. We derived that formula, right? M plus seeding function of log base 2 of m minus 2. That's the formula finding the second largest, right? Yeah. But here, n is 4, right? Yeah. You know, our current data, n equals 4. So you plug in 4. Okay? All right. When you plug in 4 seeding function log base 2 of 4 minus 2, that's equals 4, right? Yeah. That means in order to find the second largest element in the 4-element array, you need 4 comparisons. But when you go back to our current data, no, you can save 1 comparison here, right? Because you have the result of 1 comparison, right? Yeah. So this information it helps you save 1 comparison. So in the 4 comparison here, you save 1, then actually you do not need a 4 comparison, right? You only need 3 comparisons in this step. Okay? So this step, you just need 3 comparisons. So the total number of comparisons, 3 plus 3, 6 comparisons. Okay? Yeah. So that's how did we solve median of 5 problem using 6 comparisons. Recall, okay? We did this before, right? Yeah, I hope, so you can go back to look at our previous, our notes, older notes and the video, okay, if you want to. Yeah, but here, because I recall, I give you all the details, okay? Yeah. The reason I want to go through, because we need to use all the information here to solve that 3rd largest. Exactly, from all the steps we are doing here, we need to do some analogy work. Basically analogy. Okay? Because median 5, is it the 3rd largest of 5? Yeah. Median of 5 is exactly the 3rd largest element in 5-element array. Okay? So here, we did a special case of the 3rd largest element. Yeah. Then, we just go to the general case. We find the 3rd largest element in the general n-element array problem. Can we just modify the solution you see in this slide, then do some modification, we can get that solution. Yeah, so let's do it in about 10 minutes. Because we do not have much time left. Hopefully in this slide we can complete that. All right, first, analogy. Yeah. When we do the tournament method, so the step 1, tournament method. Remember, we leave 1 element out. Okay? Yeah. When we do the tournament method, we leave out x5, right? Yeah. So here, when we do the tournament method, we leave out xm. And we apply tournament method on the first n-1 elements. Okay? Yeah. Up to n-1. Yeah. Tournament method. All right? You know, all the way, yeah, to the top, yeah, because the tournament method at the end, you have a winner, right? In this tournament. Let's assume x1. x1 is the winner, but in this tournament method, to get x1, how many comparisons you need? Using our old tournament method, the number of elements -1, right? Elimination. Yeah, because to get a winner, you need to eliminate all the other players except the winner, right? So you accept all of the other elements, players, that's n-2. So this step you need to do n-2 comparisons. Because you have total n-1 elements participate in the tournament method. And to get a final winner, you need to eliminate n-2 other elements. So you need an n-2 comparison in this step. All right? Then, analogy work, because this x1, analogy work, this x1, it is in top 2, right? This x1 in top 2. Top 2 element cannot be the third largest, right? Top 2 element cannot be the third largest. So the conclusion, we eliminate it. We eliminate it. Okay? Yeah. Eliminate it. All right? Yeah. After elimination, yeah, so let's do some cleanup work, right? Can we do some cleanup work? Yeah. The step two, you know, elimination, okay. Then we do some cleanup work, all right? Yeah. x1 is gone, x2, can you use xm, the idle one? xm we leave out, so that player is idling, right? Can we use xn to replace x1, one's position, okay? And recover the tournament method. Other elements, we keep the, you know, old information. We do not throw away old information, right? We keep the old information. Okay? Yeah. So then you run the tournament method, whatever it is. Okay? Whatever it is. Okay? All right. The tournament method. But you do not need to do complete tournament method, right? So actually, you do some partial tournament method. Not complete tournament method, okay? Partial tournament method. Because a lot of work here, you already did before. You know, you just use the known information, right? The unknown part mainly related to x, you know, xn, unknown part, right? Yeah. Okay. All right. Then, because in this round, this tournament, we know, the second current largest, okay? The second current largest equals third original largest, right? Similar to our previous example. We update the goal, remember? We update the goal. The second current largest equals the third. So we just find the second largest, right? The second largest, we have second largest formula, right? Formula, number of elements n minus 1 plus seeding function log base 2 of n minus 1 minus 2, right? Yeah. But you didn't do complete finding the second largest. You did partial finding the second largest, right? And you have certain number comparison. You already know it. You do not need to do it, right? So we need to know what known information, known comparisons. Okay? Yeah. We need to know that many known comparisons. All right? Yeah. The known comparison. What are the known comparisons? Okay? Yeah. Yeah. All right. Because known comparison here, the number comparison in the first round tournament, that's n minus 2, right? Sorry. Yeah. Total number comparison in the first round, n minus 2. But we removed all the comparison related to x1. Okay? x1 related comparisons. After we do the cleanup, all the information related to x1 comparison all gone. And how many comparisons related to x1? Seeding function n minus 1. Yep. Because x1 plays this many rounds. x1, this is x1 play this many rounds. Then the comparison with x1 involved is this many. Okay? All right. That means they are the known comparisons. The known comparisons should be subtracted from that one, n minus 2 plus, sorry, minus. Subtracted from that, right? All right, so I almost get the formula. Then after simplification, we get a 2 times 2n minus 1 and plus 1 minus 1. Okay? All right, so that's this many comparison. New comparison we need to do. All right? Yeah, this new comparison. But the first round, there are n minus 2. We need to combine. Okay? So the total, the first one, n minus 2, and the second plus that one. So n minus 2 times seeding function of n minus 1 minus 3. Yeah, because minus 2 you combine with minus 1, minus 3. So this is the final formula. Okay? Yeah. Look at that. So we did analogy work. Okay? Yeah. So if you need to understand everything here, you need to get a start from the previous slide, understand the detail. Then you just do appropriate modification and repeat the same process. Then you can get the final formula here. Okay? All right? Yeah, that's it. Yeah. It's not easy, yeah, but we get it. Yeah. All right. Yeah. So that's it. Yeah.